Hello, thank you for coming. Applause already. It's actually Solr Sparse Faceting, but sorry. Before we start, I'd like to inform you how this will play out. So the funny things are in the end of this presentation. I come from as presented, the State and University Library, and you're thinking, what does a library do with data? Well, the point is that part of a job is harvesting the Danish internet 4 times a year. So we accumulate a lot of data. And of course, we store them. And recently, we were allowed to try and index them. So the researchers, they could actually find some data. And we don't have a lot of hardware or a big budget for it. So we bought the cheap machines relative to what we could get out from them. And we crammed a lot of data down in them. Fair enough, it works fine. Solr works with this without a problem. Except that the researchers actually wanted to use more than just plain search for the data. They wanted to facet on them. Problem is, as soon as you start faceting on high cardinality fields in Solr, well, whoops, those slides should have been reversed. We get response times which are less than ideal. Now, this graph, and I had to explain, at the x-axis we have the results set, the numbers of hits in the result set. And on the y-axis, we have response times in milliseconds. This is just for a single shard on our machine. And it was performed on a field that is called URL from our harvested web resources, which is basically just the address of the resource. We have 200 million of those in a single shard. And, well, this is what happens. So I'd like to go back to the slide I just skipped over and say, what is it that happens when you facet? Well, faceting in Solr is, for strings is really extremely simple. It only has 3 phases, at least with 1 shard. We allocate a counter. That's the first line. Then we run through all the results, all the documents in our results, and extract references to the terms in the facet that are in the results, and we increment the counters, which will give us a counter structure like the one to the right. And when we have finished incrementing all the counters from our result set, well, we extract the top 10, 20, 100, 1,000. I don't know what we need. So it's a simple thing. But while it works very well for a few million values in this facet field, as we can see, we do have a bit of a problem with this 200 million cardinality thing. One of the problems is that such counter structures tend to be fairly large. So when we're doing this, these requests, these are, by the way, 3 threads that are hammering at the same time, just to stress it a bit. What we have here on the blue line is memory usage, and what we have down in the bottom is garbage collectings. So, and the light bars at the bottom, those are what you call it, normal garbage collections, and the darker ones are the full garbage collections, which means a pause in the request. So that influences the result a lot, and I must say account for a lot of the fluctuations in the response times. Now, I'm sure that somebody could tune the garbage collector a lot better than we can, especially since we haven't tuned anything at all. We're just using the default one. But the thought is, why do garbage collecting at all? Well, if you remember the old code, there were 3 phases. Allocate a counter, fill the counter, extract the top X result. OK, simple idea. Let's just allocate a counter from a pool, fill it, extract, and then deliver it back to the pool. And then reuse it on the next call. Of course, we need to clear the counter between the calls, but it turns out that's a lot cheaper to do than reallocating it from the heap. So what we have here on the left is standard behavior with the memory and the garbage collectings. And what we have here on the right is the behavior of the garbage collector after we have turned this thing on. Still not perfect. There are some ugly spikes, but we'll get to that. Response times. I know this is messy. It will be better. So the blue stuff is standard Solr, and the pink stuff is, well, when we reuse the counters. I cannot make head or tail of this. So if you switch to this visualization instead, you'll see this more than once in this presentation. In each of these boxes, we have the quartiles. So the top of the box is if 75% of the request will be served below this amount of time. And as we can see, the blue boxes, again, is without reuse of the counters, and the pink boxes are with reuse. We get a better, a smaller spread in the response times, and the median, this is the black line, is moving downwards. So it seems to help. Now, there's a slight interesting thing about this, because if we look at the response time with the minimum at the very bottom of these candlesticks, it starts at 500 milliseconds, even for the very small result sets. So, why is that? Well, the point is, in our third part, which we repeat, allocate counter or reuse a counter, update the counter, then extract the top X results. We actually iterate all the counters to the right to extract the top 25. That's a problem if we have 200 million counters. So the next step we want to do is to say, well, if we knew which counters were updated, we could only count those when we needed to extract the top 25. So, for this, we'll be making a tracker besides the counter. We have the tracker from the start. It's empty. And we update one counter. That was counter 3 in this case. Good. What we do here is say, OK, counter 3, it's updated. We'll just put 3 in the tracker. So now we know counter 3 is updated. We do another update. That's counter 1. And the tracker says, now we know counter 1 is updated. It's quite a simple principle. We update counter 3 once again. But hey, it was already updated, so we don't need to update the tracker. And we go on. When you have finished this collect all the counts phase, we now have a tracker, which gives us exactly the counters which has been updated. And it looks like this in the code. The yellow parts are the new parts of the codes which changed from the previous one. By the way, I might add, we are very, very quickly exiting standard Solr land now. I won't go through the code, but as you can see, it doesn't take much to add this counter method. There's, of course, a downside to counting. It introduces an extra step in updating the values, which has a speed penalty. And it introduces a memory overhead, which depends on how large you want to count. We have found out that about 8% of the counter size works fine for this tracker mechanism. Beyond that, there's really no win in it. And the speed penalty, well, again, as long as the tracker is below a certain point, we win. So, this is a result. The blue stuff is when we do not use this sparse faceting, which is all above the 500 milliseconds response time. And the pink stuff is when we turn on the sparse. This looks like a hockey stick. Now, the good thing about this is that this area, well, I can't use this. We have here, down in the middle, where everything is good and perfect, and we have this area where things tend to go south for the very large result sets. Luckily, most queries tend to be down in this very low area. Well, depending on your corpus and your search patterns and all that. So we're happy. We removed the garbage problem, or at least minimized it. We got the response times down. So, and this works. But in these days, no Solr is alone, practically. It's all in Solr Cloud. What happens in the Solr Cloud? Well, there's an extra step to faceting when doing cloud searches. We have a phase one. It's exactly as a single shard setup. Do the facet call, maybe ask for a bit more facets than the one you request because, well, statistics and all that. But basically, do a standard facet call. Then the calling node gets a result back. It merges them. It calculates the top 25, whatever we use. And then we have this small problem that we are not sure that we have the right counts, because some of the shards might not have returned a count for the term that was in top 25. Good? So the simple thing is, well, the merger says those shards that did not deliver a result for one of the top 25 terms, or more of them, well, they get to recount them. The way that is done in vanilla Solr, we see in this code section here, pseudocode, of course, I'm lying a bit. But it's really simple. We just, for each term that we need the find count from in the shard, we perform an extremely simple search, which is just for the field with the term, and then do an intersection, I think the word is, with the full result sets. Well, it works, but it has a peculiar property. Excuse me. See, now these are response times again. This time we have switched to cloud mode. We have 9 shards here, but on the other hand, just to scale it down, scale up in shards, scale down in faceting. Our field now only has 1 million values. It's a domain field in our index, by the way. To the right, we see this natural, well, as the count goes up, well, the response time goes up. But what is happening in the middle? Because all our nice response times, which were down below 50 milliseconds, well, we have a lot of them up in the seconds. That's pure statistics. If you have 9 shards that deliver results, and we have very small result sets, well, chances are that each shard has returned less than the top 25 it was asked. It has returned a complete set of facets possible for this result set. And in that case, it won't be asked again, because the merger knows it has no more information. That's over here to the left. When we have more hits, well, we have the opposite situation. The chances are that the top 25 terms from each shard will be the same. And as they have already delivered count for that term, there's no need to ask them again. So be happy here. But in the middle, we have this pit of pain, which was coined by Andy Jackson from the British Library, which unfortunately means that statistically, nearly every term needs to be fine counted from nearly every shard. And if we have a top 25 and we have 9 shards, it's, I don't know, about 200 requests that we need to add, or these requests have a lot of these intersections. So that's bad. One solution, which actually works pretty well, is not to find count. But for this talk, we are focusing on getting exact results. What if we made it more efficient to find count? Because as we remember, faceting, the first phase of faceting was quite fast. So we could just repeat that. And then, as we have the counts, iterate each term one at a time and just look it up in the counter structure, which we have now. Okay, that works. That was level 1 of this. Until we realized that actually we already did the counting in phase 1. If you just remember the results, the counter structure from phase 1, all the counts are there. So we just need to take it from our pool and then get the counts directly. Sounds efficient? And it is. So By doing this little trick, looking up in another way, we are virtually eliminating this pit of pain, this large hill in the middle. That was about it for performance. Now, we had our setup. We had 200 million values. And it's all about the memory. And the worst thing is that URL is just one of our fields. One other field we really like is the links, outgoing links from web pages, which has 600 million unique values per shard. And it's reused a lot, so we have about 6 billion references from documents to these values. Now, the number of references doesn't really matter with regard to memory. I'm just mentioning to get the complete picture. But the cardinality of the terms certainly matters, as well as how many documents a single term can belong to. Well, we still want to facet on this if it's possible, because the researchers would like to build nice graphs between web pages in a quick and responsive manner. So, and we don't want to allocate a lot of memory. So maybe we could look at that. See, if you try and explode such a facet field, we have 3 examples in our corpus. One was the domain, which is fairly low cardinality with the 1 million values. The other one was URL with 200 million, and the third one were links with about 600 billions. This view, this histogram view, you can see it directly in the Solr admin front end, and I really recommend it. It says a lot. What it says, among other things, is that we have a lot of values which only count to 1. They're unique in the index. Only a single document has them. That's the one on the top. What we can also see, I'm sorry, I don't think half of you can see that, is that at least for links, well, we have a few values that are referenced a lot of places, which is about, by a lot, I mean 2% of the pages or something like that. I think it's the Google tracker thingy or something, or robot.txt, I don't know. So, how are these represented? Well, ideally, in an ideal world, the Platonic ideal of a counter, well, if we have at the bottom the different terms, at the top we have some bits needed to count them. We can see here that term A only requires 1 bit because there's only 1 page that has them. Term B requires 3 bits, so we know there's at least, what is that, 5? 7. There's a maximum of 7 pages that points to it. We know these maxima because, well, it's an index. We can just analyze it. But this ideal world has little to do with reality. No. How it's represented in the classic vanilla Solr is simple. We just allocate 1 integer to count each term. OK, it's not a problem with low cardinality because who cares if it's, I don't know, 1 megabyte or 2 megabyte. But when we're talking about a cardinality of 200 million, then we suddenly have a counter structure of nearly 800 megabytes. To make matters worse, we need 1 counter structure for each concurrent request. So, well, it all counts up. First thing we did was pretty simple. If we look at the structure to the left, this, by the way, goes to 32, which is above the slide, to visualize the wasted space in red. Well, we can see that the highest counter in this example only takes 11 bits, but we used 32 bits for all the counters. That's a waste of space. So, simple enough, we just use 11 bits for all the counters. That's the maximum we will ever need to count. It works fine. If we look at the statistics from our sample chart, we can see that, well, for URL, which is a nice fit, we get it down to half the memory usage, and for links, which is a better fit because we have very high counters, a few very high counters, we only get down to 75% of memory usage. So not really a game changer. So now we come to the fun part. Because as everything red is wasted, let's try and minimize that. This is an idea that I called n-plane counting, in latter for better name. It really, in principle, is very simple, and it doesn't really work, which we'll see later. But we need this as a building blocks for the next step. What we have down here in the bottom is simply the first bits of all the counters. That's plane 1. If we look at the ideal over to the left, well, every counter needs at least 1 bit. Fine. So we have them on the right too. Now, for all these counters that needs more than 1 bit, we keep track of that by having a second, an overflow bitmap on top. This is the blue line. For every slightly darker blue square we have here, that means that the counter it belongs to continues on the upper planes. Okay, this is something, the blue structures are static when we open an index, we can construct them. So how do we use this? Well, this is the same illustration as before. I'll try incrementing a counter here, in this case, counter L. So, first time counter L is visited, we just set the bit at the first plane. Simple enough. Now counter L is visited again. What happens is, we visit counter L. Okay, it's set. That means we need to set the next bit higher up. Well, we can see that it overflows. Hopefully it should, because else we'll have an error. And we count from the left with the blue bits that says 1, 2, 3, 4, 5. Okay, we go to plane 2 at entry 1, 2, 3, 4, 5. We know that L continues here. So that was simple. And that means we know where to set the bit number 2, because we counted to 2 now. And when we count to 3, well, then we just put down an L, and so on, so forth. So now we count it to 12, and it's represented that way in the planes. To make this work, we need to be really quick at counting these overflow bits. Fortunately, there's a function called rank, which with very little overhead, 3% of memory, does that in constant time. So no worries there. The problem was that it did not work, because we used tracking. You remember the tracker? It's very simple. If the previous value of the counter was 0, update the tracker. But how do we know that the previous value of the counter is 0 in this scenario? Turns out we don't. Because with this setup, when we have counted to 12 and we try to increment L again, we cannot see if this is 0, represents 0, or something else, unless we read all the way up in the planes, which is dark slow. What do we do about that? Well, we introduce a +1 and 1.5 bit plane. Good, you got it. This, performance-wise, it will work, I can tell you. Memory-wise, it has a worst-case overhead of 1 bit per counter, which is what it is. Fortunately, as we remember, most of our counters, 2/3 in this when we're talking about links, were really only 1 bit. And all the 1-bit counters, they take up exactly as much space as in the previous version of this structure. So it's really all the counters that are above 1 that takes this 1 extra bit hit. So what we have here in the bottom plane is one that keeps track of is the counter 1 or more. And above that, we have the standard counters. That was confusing. Fortunately, we'll just do the same example. OK, we visit counter L. We update it once. We set the bit. We are happy. We update the tracker. Now, we try and update counter L again. In this case, we see, oh, this bit is already set. Let's not touch that. Instead, we move up at once, do the counting thing, and update the entry up in the 1.5 bit plane. So this bit pattern, confusing as it may seem, actually represents the number 2. It's 1 plus 2 power to the power function of 1 minus 1. So Up here in plane 2, 3, and 4, we have a standard bit representation, binary bit representation. And in the bottom, which simply has a flag saying +1. So let's update it once again. We hit the L. We don't touch that. We go, sorry, in plane 1, we go to plane 2 and see, OK, there's a set bit. We need to change that bit pattern to 2. And this gives 3s again. So we update L once again, and all that, up till we have 12, well, which is represented in this funny way. OK. Now, this is all well and good, but it's a lot of hoops to hop through. So what does it give us? Well, the point is it's quite a massive space saving. If we look to the right and see for links, which of course is our poster child for this, we get it down to 300 megabytes to count 600 million values, as opposed to if we had just used the integer counter in plain vanilla Solr, which would be above 2 gigabytes. OK. There are more good news. As we remember that the blue stuff, the overflow bits, they were actually static. They never changed. So that really means that if we need another counter, because we have multiple concurrent requests, we only need about half the space. So that means that in slightly less than 200 megabytes for the extra counters, we can do the counting of these 600 million values. OK. Nice, we saved memory. How hard does it hit us performance-wise? Well, here are 3 comparisons. The blue one is the integer representation. The purple one was the maximum bit representation, which used the structure called packed in from Solr. And the green one is the end-plane representation. And as we can see, not surprisingly, there is an overhead with using this end-plane representation. But on the other hand, we can actually do it in with quite little memory. So we have all these nice stuff, these nice things. So, and we have this little cluster. Let's try and combine it all, see what happens. So we have these 3 fields, domain, URL, and links with its cardinality. We also have 9 shards. And in order to get a little thing going, we're just hitting it with 3 concurrent requests. Oh. Well, the problem is that what we have on the y-axis is actually moving into minutes. No, not on this chart, but it keeps going. We have a worst case of, I don't know, 5, 10 minutes. So that was not so good. On the other hand, we can get by with this faceting on this one of the shards with 8 gigabytes of heap memory for 900 gigabytes of shards with this. So we now have 2 situations. We have fast for smaller cardinality, by which I mean below 200 million. And we have memory saving for higher cardinality, and we can use that. That's not all. There are tricks, but frankly, I don't think I have the time to go through them. Instead, I think that I will, let's see, try this at home. Now, silence and blank stares. Any questions?